Okay, so today what we're going to do is we're going to discuss a pictorial approach to understanding particular spacetimes, that is manifolds with certain metrics. Okay, so in Minkowski space, that is in special relativity, where you have the flat metric eta, spacetime diagrams, we already know that they're valuable tools for visualizing the spacetime. And if we want to understand things like its causality structure, and what do we mean by causality structure? Past and future light cones of every point. Why is this important? Well, if you want to know in special relativity, it's important to know what regions of space can influence or be influenced by events occurring at a particular space-time point. So for example, in standard Minkowski space, if I draw my x and t coordinates and I draw this point here, then we know that if we know the light cones, okay, so we know that this is, let's say, the interior of the future light cone, and this is the past light cone. Then we know that if I'm interested in this particular space-time point O, then only things within the past light cone could actually influence anything that happens at O. Okay, and similarly, O can only influence things within its future light cone. It can't influence points outside of its future light cone. So if I turn on a switch at O, that effect of turning on that switch can only be felt within the future light cone. No signal can reach these other regions. So these regions are space-like separated from O. Okay, and the future and past light cones are time-like separated from O. And points on the light cone itself are null separated. Okay, the proper distance ds square is 0 along this from any point O to any other point O prime along this null light ring. Okay, so this really was a very useful pictorial way to understand Minkowski spacetime and especially to understand its causal structure. So some features of this particular diagram are that we arranged our coordinates so that light travels at 45 degrees, right? So the simplest thing we did was rescaled C so that, or we think of this as we're plotting CT, okay? So we could think of it as rescaling our time coordinate so that we are light rays are always travel at 45 degrees. The second is that these, as we've already discussed, the future or past light cones tell us the causal regions. Okay, they tell us for every space-time point we can draw these light cones, and they tell us what regions can influence that point, what regions can be influenced by that point, and what regions are causally disconnected from that point. Okay, so in particular, this idea of space-like, time-like, and null separation of space-time points can be pretty easily seen from the space-time diagram. The other thing is to be really clear what we have done. Okay, if we draw t and x, okay, and we're in 4D Minkowski space, that is 3 + 1 dimensions, then what we have really done is we only plotted a 2D slice. That is, we had to fix y and z to some values, okay, without loss of generality, let them be 0, 0. And so we're only looking at a 2D slice of 4D spacetime, okay, where the 4D spacetime has signature -1, 1, 1, 1, okay, or this 2D projection has signature -1, 1. In the t and x coordinates. But what we are doing is we are drawing that 2D space-time in Euclidean space, okay, which means that on this paper, distances are not measured using Euclidean distance between these 2 points, but distances really have to be measured using this Minkowski metric. Okay, so if I have a point at Tx and T prime x prime, the proper way to find the distance between these two is not to just take a ruler and measure off that distance, but rather you must calculate something like t minus t prime whole square minus x prime whole square. Okay, or for infinitesimally separated points, you need to calculate this quantity. Okay, and that gives you the proper distance. Okay, or with the metric convention that we're using, we should use minus. Okay, and this gives us a measure of the distance or the distance square between these two spacetime points. So the 2D diagram is really only representing the coordinates of spacetime points. Okay, and the metric or the distance measure between these two spacetime points can be inferred. Okay, if you know the metric. Okay, but that's not the main thing that we're interested in. Okay, the details of the metric are not really what we're interested in. Okay, but you can interpret those distances if you want to. Okay, but we're more interested in the coordinates, okay, of all these space-time points and the causal structure. in this diagram. The other thing is that because of the rotational symmetry of Minkowski space, okay, the fact that X, Y, Z have a symmetry of rotations, we can easily imagine what the other slices look like. Okay, just by looking at this slice, we know that, for example, if we spin this about, in the XY plane, right, we would get X and Y. Okay, and for any XY slice, okay, or any axis along in this XY plane, or in general any axis in the XYZ direction, so if I now plot in the T versus n hat direction, n hat is a direction in space. Okay, we expect that the space-time diagram, because of the rotational symmetry, looks the same in the T n hat plane as it does in the TX plane. Okay, so drawing it in the TX plane tells us about what the full structure of the space-time in all directions, okay, because of the rotational symmetry. So we can easily visualize the other 2D slices from this diagram. Okay, and one thing that is hidden in this diagram is the asymptotic behavior. That is, what is happening as t goes to plus minus infinity, or as x goes to plus minus infinity, what is happening? That is sort of hidden from us, but of course, we can extrapolate and say what happens, but strictly speaking, we're not reaching t is infinity in this diagram, right? This is drawn in a finite range of t and x. Okay, so now the idea is that we understand these space-time diagrams from Minkowski space pretty well. Okay, what we'd like is a similar visual tool, but to represent more general spacetimes, not just Minkowski spacetime, but more general spacetimes. Okay, obviously for very general spacetimes which don't have symmetries, you cannot do it, right? Because how do you represent 4D space on a 2D sheet? However, if there is a certain amount of symmetry, then you can do this, okay? And those diagrams which you get are called Penrose or conformal diagrams. Okay, there isn't, okay, at least in the literature, typically there isn't a very clear specification of what, some systematic procedures to get a Penrose or conformal diagram. But I'll give you some rough list of ideas, and this list is common to almost any textbook presentation that you'll see. I'm going to follow Sean Carroll's presentation. Okay, and we'll follow and we'll try to understand what are the main features of a Penrose or conformal diagram, and we'll also see that the diagram itself is not unique. Okay, there are many equivalent choices or different choices that you can make, which also constitute broadly the definition of what are called Penrose or conformal diagrams. Okay, but we'll see what the essential things are that we require of such diagrams. Okay. Okay, so the first criteria is that we need a sufficiently symmetric spacetime. What is sufficient? I'll leave it open for the moment because there might be counterexamples to any specific rule that I give you. But roughly, let's take for the moment rotational symmetry. Okay, and how is rotational symmetry defined for a general spacetime? Well, you need to talk about the Killing vectors. Okay, so we assume that it has a Lie algebra. The Killing vectors have a Lie algebra of let's say SO3, which means that the 3D rotations are present. Okay, this could be an example of an assumption of the symmetry of the spacetime. So what we would like to do with our diagrams is we'd like to capture both the global structure of spacetime. That is, we'd like to see the full spacetime at once. Okay, and the second thing we'd like to do is to capture the causal structure. Okay, so by global structure, what we mean is, normally when we draw manifolds, we said that you have to cover them with different coordinate patches, right? And the thing is, if you're drawing a space-time diagram which captures the global structure, you need to capture the effects of all coordinate patches, or at least a complete covering of the manifold M needs to be captured in this space-time diagram. Okay. The second thing is you want to capture the causal structure, which means you want to understand the light cones. Okay, that is, you want to understand null geodesics. Okay, so if you can understand the null geodesics, then you understand the causal structure. Okay, because roughly things contained within the the null geodesics will tell you the light cone, and within the light cone you can construct what is the future and what is the past. Okay, so for the global structure, what we'd like to do is we'd like to capture the entire space-time by bringing the entire space-time to some kind of finite coordinate range. Okay, so we're not satisfied with the fact that with these space-time diagrams that we drew from Minkowski space, because they sort of have an infinite extent. Now, in this Minkowski space-time is quite trivial in the sense that you know what will happen at infinity, but still, Okay, we'd like to bring the entire Minkowski spacetime, shrink it down to a finite range. And the second thing that we'd like to do is we'd like to capture the causality structure. And this we will ensure that we will make a coordinate change to bring the entire Minkowski spacetime within a finite range. But we want to still ensure that light rays travel at 45 degrees in the diagram. This was a nice simplification, which tells us that the light cones are always like these 45-degree type cones. And we'd like to keep this structure, okay, in our spacetime diagrams. So essentially, these are the two key features that we demand of a Penrose diagram. Okay, so the idea is we want to make an appropriate coordinate transformation that captures the global structure of the spacetime and as well as preserves the causal structure. That is, it preserves the fact that light cones are at 45 degrees. Okay, so both of these requirements can be accomplished by a clever choice of coordinates if you have a sufficiently symmetric spacetime. Okay, so let's say the sufficient symmetry condition is that you have the killing vectors have a Lie algebra of SO3, or that is that there's a rotational symmetry. Okay. However, the choice of coordinates that you can use to construct the Penrose diagram is still not unique. There are many choices which will capture the global structure and which will preserve this causality structure. Okay, so the choice of Penrose diagrams are not unique. It depends on which particular coordinate transformations you choose within that overall freedom that you have. Okay. So the easiest way to understand Penrose diagrams is just to do an example. So we'll spend the majority of the time we'll just look at Minkowski spacetime and we'll try to understand the Penrose diagrams for Minkowski spacetime. And then maybe towards the end, I'll show you some Penrose diagrams for other spacetimes, and then we'll see, how these can be understood. In particular, I'll show you for Schwarzschild because we already understood the Schwarzschild metric. Okay, so let's look at Minkowski spacetime in 3+1 dimensions. Any questions here? Sorry, go ahead. Okay, so in Minkowski spacetime, this is the line element, right? And you can construct a metric from this. That's minus dt squared plus dr squared plus r squared d omega squared. Now the structure, this r squared d omega squared, this is what's ensured by the rotational symmetry. Okay, so there's some coordinate system in which you can write it like this, where d omega squared is the line element on the 2 sphere, okay, which is d theta squared plus sine squared theta d phi squared. And here the range of coordinates is such that t goes from minus infinity to infinity, r goes from 0 to infinity, and theta, of course, goes from 0 to pi, and phi goes from 0 to 2 pi. Okay, now strictly speaking, we've seen that, okay, this is really something like this. We can't really go to theta is 0. We can't really go to theta is pi. I mean, in the sense that you need to use a different coordinate patch to capture the north and south poles. R is equal to 0 is strictly not part of the coordinate patch. Okay, but we know what these things mean. Okay, we know what it means to include R is equal to 0. We know, I mean, it's a coordinate singularity. Okay, in the sense that, okay, this R is, if I take R to 0, then no matter the angular separation, the distance measure goes to 0. But it seems like coordinate singularity, but we understand exactly why that's happening, right? Similarly, theta is 0 and theta is pi not being included. We understand why they're not included, but we also understand that you can include them if you just increase take a different coordinate patch. So we won't worry about the fact that these things are not, I'll use less than or equal to, but we understand that strictly speaking, these are not part of, a single coordinate patch. Okay. Okay, now let's look at the spacetime diagram in the t versus r plane. Okay, because we have this rotational symmetry in theta and phi, we'll just look at t versus r. So if we just look at t versus r, okay, these are what the light rays look like. Okay, the light rays will satisfy ds square is 0. Okay, that is the distance between any 2 points will be a null geodesic, and the distance along the null geodesic will be 0. So we'll have dt square is equal to dr square, or dt is equal to plus minus dr. Okay, so in other words, you'll have this condition. Okay, so you'll have this condition. And if dr by dt is negative, then you have what are called incoming geodesics, radially ingoing geodesics. Okay, so these are going radially inwards. And then if dr by dt is positive, that is r is increasing, then these are outgoing geodesics. Okay, outgoing null geodesics. So if I have a light ray coming in from infinity, so it comes in along this blue line here, and then at r is equal to 0, okay, this is not really bouncing off. Okay, this is just going towards r greater than 0. So in 3D, what is really happening is it's coming in and then reaching r is equal to 0 and then going out in the opposite direction. Okay, so that's what's happening here. So this is an x, y, and z. Okay, and this, as a function of time, it keeps moving this way. Okay, so this is what the incoming geodesics look like. These are what the outgoing geodesics look like. Null geodesics, that is. Okay, this is what light rays would do. Okay, in these coordinates. So null radial light rays are all at 45 degrees. Okay, r is equal to 0 is not strictly covered by the coordinate patch, but we also understand, okay, why you can actually secretly include it. Okay, I mean, yes, strictly speaking, you cannot include it, but we understand what it means to include it as well. Each point on this diagram, so if I take any point here, okay, specify the TR values, then secretly speaking, there is also a whole collection of theta and phi values associated with this. Okay, so in other words, there is a two sphere associated with each point on this diagram. So each point in this diagram has a two sphere. If I think about one extra dimension, that is, let me imagine that it's r and phi. Okay, so imagine that it's just x and y directions. So there's an r and a phi, which tells me my x coordinate and my y coordinate. So I could imagine something like this, that, you know, there's a circle associated with each point in that case. Okay, that circle, if I want to visualize it, is easy, but by sort of spinning this diagram around like this, there's a circle associated with each point. Or I could think of this as x and then there's a y. Okay, so more generally, instead of an S1, okay, that is a circle, we'll think of a sphere, an S2 associated with each point. Okay, and that's obviously you cannot draw it on paper, right? That's two extra spatial dimensions that you need to draw. So each point in the diagram has an S2 associated with it. So for example, if I take the point t is equal to 0 and r is equal to capital R, so let's say this point here. Okay, so what does that two sphere represent? Well, it represents a spherical shell of radius capital R centered at r is equal to 0 at the time t is equal to 0. Okay, so that's what we mean by this two sphere at t is equal to 0 and r is equal to r. So any particular point on this diagram, right, has an S2 associated with it. Okay. Okay, so now what we're going to do is so this satisfies the second criteria that we want for Penrose diagrams, that is the light rays travel at 45 degrees, but it doesn't really satisfy the main criteria, the first criteria of this global structure of the space-time. Because again, I mean, t goes off to infinity and minus infinity, r goes off from 0 to all the way to infinity, so it doesn't capture the full structure of the space-time. So we'd like to shrink all of that and bring it into a finite range. Okay, so one attempt to do this is to bring in the coordinates to a finite range. You can use, for example, an arctan function or tan inverse function. So what the tan inverse function does is it takes things from which range from minus infinity to infinity, and it shrinks them into a finite range between minus pi by 2 and pi by 2. Okay, so the tan x graph, for example, looks like this between minus pi by 2 and pi by 2. Okay, it goes from minus infinity to infinity. And so if you just invert that graph, okay, you get this tan inverse function. So tan inverse basically squeezes the entire rail line into this region minus pi by 2 to pi by 2. Now, why tan inverse? You could use any function that squeezes you in this range minus pi by 2 to pi by 2, or it could be squeeze you into any other range. For example, you could use a tan hyperbolic function. Okay, as we've seen in special relativity, tan hyperbolic, right? Tan hyperbolic of rapidities. Rapidities go from minus infinity to infinity. They scale you to a finite range in v by c, which tan hyperbolic is between minus 1 and 1. Okay, so mod tan hyperbolic is less than or equal to 1. Okay, so you could have used tan hyperbolic, you could have used arctan. So there are many choices. Okay, this choice is not unique. which is why the Penrose diagrams are not unique. Okay, but all you want to do is essentially compactify that entire range. So the first guess that we'll make is let's compactify this time direction by defining a new time variable t twiddle, which is tan inverse t, r twiddle, which is tan inverse r, and we'll leave theta and phi unchanged. Okay, so what is the range of t twiddle now? It goes between minus pi by 2 to pi by 2. R twiddle goes between 0 to pi by 2 because r only went from 0 to pi. 0 to infinity. Okay, so we can also take dt. Okay, so we invert this relation. So t is equal to tan t twiddle. We differentiate this. So dt is dt tan twiddle, tan t twiddle, which is secant square t twiddle dt twiddle. Okay, and similarly dr will also be secant square r twiddle dr twiddle. So if I now want the metric in these t twiddle and r twiddle coordinates, okay, so I'll evaluate the line element again, ds square. This is the same line element of Minkowski space. So dt square minus dt square is secant to the 4 t twiddle dt twiddle square. Okay, so I just squared this. And dr square, so that plus dr square will be plus secant to the 4 r twiddle dr twiddle square. And now I also have to replace the r square d omega square. I have to replace this r by r twiddle. So I'll replace r by tan r twiddle. Okay. So this is the new line element. I mean, the same line element expressed in the new coordinates. Okay, that is the t twiddle and r twiddle coordinates. And now if we have a radial null ray, okay, we know that ds square is 0. But now what we'll have is, so if we assume that the angle is not changing, okay, so this is purely moving radially, then we're fixing theta and phi, and if we set ds square to 0, that will tell us dr by dt twiddle, that is we equate these two terms, the sum of these two terms to 0, and that will tell us dr twiddle by dt twiddle is plus minus secant square t twiddle by secant square r twiddle. Okay, and this changes, okay, if t twiddle and r twiddle are changing, so different t twiddles and different r twiddles, this value changes, so it's not always plus minus 1, which means in the plane of t twiddle and r twiddle, so they now have a finite range, and that t twiddle goes from minus pi by 2 to pi by 2, r twiddle goes from 0 to pi by 2. But light rays don't travel at 45 degrees on this plot. Okay, they travel at, they will keep changing the angle at which they travel because this quantity keeps changing. Okay, on the diagram. So light rays, I mean, they might do something like this. Okay. So that's not very helpful. Okay, because although we got the global structure of the spacetime, okay, that is we captured everything in a finite region. Okay, we lost out on the causal structure. Okay, that is light rays no longer travel at 45 degrees, and so this curve is kind of complicated to evaluate. You have to integrate this equation. So it's a bit messy. Okay, so what we'd like to do is a coordinate transform that preserves both the global structure and the causal structure. Okay, we only accomplished the first part, which is to get a finite range of coordinates, but this change of coordinates doesn't preserve the global structure. Okay, so it doesn't preserve the causal structure. So what's the alternative? Well, okay, hidden in here is a strategy for what we need to do. Okay, so the choice is, since we want to preserve the light cone or the null geodesics, what we'll do is we'll take null coordinates. Okay, that is, null coordinates are the ones for which, so for example, you define u as t minus r and v as t plus r. Okay, we did something similar for Schwarzschild black holes. Okay, so now we can look at the range of coordinates for u and v. Okay, range of these coordinates u and v. And u goes from minus infinity to infinity, v goes from minus infinity to infinity. But u is less than or equal to v. And the reason is that for a given t, I'm subtracting r in u and I'm adding r in v. And r is a greater than or equal to 0 quantity. So that means that u is always less than or equal to v. Okay. So, and where does equality occur? Well, equality of u and v occurs at the point where r is equal to 0. Okay. Okay, so this is good. Okay, so we can use, so the idea is that we'll switch to these null coordinates. Okay, these null coordinates extend over an infinite range. But now the point is that we will shrink these null coordinates, okay, into a finite range. Since we're using null coordinates, we expect that we will preserve the causal structure, okay, because u is equal to constant is a geodesic, v is equal to constant is a geodesic, okay, a radial null geodesic. So so if we shrink these, okay, we still preserve the null geodesics, okay, so we still preserve the null geodesics. There will still be some u prime is constant, and or capital U is constant, and some capital V is constant, okay. Where this capital U is a shrinking of this small u, and capital V is a shrinking of small v. Okay, so so if we choose capital U to only be a function of small u and capital V to only be a function of small v, in particular, we'll choose capital U is equal to tan inverse u, capital V is tan inverse v. Okay, then constant u's will also be constant capital U will also be constant small u, and this will also be constant capital U's will also be null geodesics. Okay, so that's the basic idea, that we'll use null coordinates and we'll shrink the null coordinates to a finite range. Okay, and that should give us both the global structure as well as the causal structure. Okay. Okay, so let's work it out. Okay, so this is T, this is R. Okay, and if I want to get let's say the U is equal to T minus R and V is equal to T plus R. So these curves, okay, that is the blue incoming geodesics, null geodesics, these have V is equal to constant. Okay, all of them have V is equal to constant. Why? Because for all of them, T plus R is a constant. Okay, so if you draw the line T plus R is constant, okay, they will have negative slope. Okay, that is T is equal to minus R plus C. Okay, so these are lines of negative slope -1. Okay, so these are these lines. So these are ingoing null geodesics. Okay, that is the light rays are moving inwards. Okay, and similarly, the lines with T minus R is equal to constant, that is constant U. Okay, constant U. These are outgoing geodesics because they will satisfy T is equal to R plus constant. These are the same as U is equal to constant. So these yellow lines, okay, are U is equal to constant. These are outgoing geodesics, null geodesics. Okay. Now, how do I find what the value of U is for a particular outgoing null geodesic, or how do I find the value of V for a particular incoming null geodesic? Well, at the point on the t-axis, right, at this point, U is equal to T minus R, V is equal to T plus R, but R is equal to 0, okay, on this axis. So U and V are just correspond to whatever is the t coordinate here. Okay, so if this yellow line intersects the t-axis here, I just read off the intercept on the t-axis, and that is the value of U for this outgoing null geodesic. Similarly, for an incoming null geodesic like this one, okay, I will just read off the intercept on the t-axis, and this is the value of V, okay, for this geodesic. Okay, so clearly as I go this way, okay, along these blue curves, V is increasing, and clearly as I go along this way, okay, U is decreasing. Okay, because the intercept is decreasing, okay, as I go this way. Okay, and the other thing now is that if I look at points for which U is equal to V. Okay, the points with U is equal to V. Okay, those points are only at R is equal to 0. Okay, those points are only at R is equal to 0. So only these points have U equal to V. Okay, and at R is equal to 0, basically this point has the same U value. This curve has a constant U value. This curve has this null geodesic has a constant V value. And at this point, okay, and both of these have the same, so this has a value U is U naught. This has a value V is V naught. And they both happen to be the same. Okay, U naught and V naught are the same for the curves which intersect at R is equal to 0. Okay, now we've already said that each point here represents an S2. Okay, what is the radius of that S2 in the UV coordinates? Well, we have to express R in terms of V and U. So R is half V minus U. So in terms of V and U, the radius of that S2 is now half V minus U. Okay. So what we want to do now is the first thing we want to do is re-express our Minkowski metric in terms of these UV coordinates. So when we do that, what we'll get is ds square is equal to minus half du dv plus dv du. Okay, actually this is just minus du dv. Okay, the reason we split it into two terms is because we have to write this metric in this symmetric form. Okay, but it's just minus du dv plus the whole thing is just minus du dv. And then this other part is r square d omega square. Okay, how did I get du dv? Well, I have minus dt square plus dr square. Okay, and du is minus dt plus dr. dv is minus dt minus dr. Okay, so when I square them, I get dt minus dt square plus dr square. Okay. Sorry, did I get that right? Sorry, it's dt minus dr and dt minus dr and dt plus dr. Okay, so when I square them, I get dt square minus dr square, and there's an overall minus sign. Okay, so this is why this is the same as the Minkowski metric. This part is dt square plus dr square, and this part is r square d omega square. Okay, so we've got the entire metric expressed in terms of these light cone coordinates. And now what we want to do is we want to bring u and v into a finite range. Okay, so we'll define capital U and capital V as tan inverse U and tan inverse V to bring them in from minus infinity infinity down to this finite range of minus pi by 2 to pi by 2. So capital U and capital V will now be between minus pi by 2 and pi by 2. Okay, and capital U, because small u is less than or equal to small v, capital U will be less than or equal to capital V. Okay. Okay. So now we have, if we differentiate, okay. So again, we'll differentiate, okay, and we'll express small u in terms of capital U and small v in terms of capital V. And so we'll get small du is equal to secant square u du. Small dv is equal to secant square v dv, similar to what we've done before. Okay, except we were not using null coordinates before. And v minus u whole square, which is this quantity here, we want to express in terms of capital V and capital U. So we write it as tan v minus tan u whole square. Okay, and so tan v is sine v by cos v, and tan u is sine u by cos u. So I'll take the common denominator, and I'll pull out 1 over cos u, 1 over cos v whole square, which is secant square v, secant square u. What I have left inside the brackets is sine v times cos u, where I multiplied this denominator with the numerator here, and sine u times cos v, where I multiplied the denominator of this with the numerator here. Okay, whole square. And this is now secant square v times secant square u times, now this quantity in brackets can be simplified using a trigonometric identity. This is sine v minus u. Okay, and then the whole square, so sine square v minus u. So now basically everything in the metric here we want to replace in terms of capital U and capital V. Okay, so ds square will now be expressed. Yeah, okay, so we had this already, the small du, small dv. So the product of small du, small dv, which was what showed up in the metric here, can be replaced by secant square u, secant square v, capital V, times d capital U, d capital V. Okay, so and then I spread it again into two terms, so I can write it like this: minus du dv plus dv du, and then there's a factor of minus 2. And then there's secant square v, secant square u is the prefactor. Okay, so this is just telling you that the overall factor is minus half. Okay, but then it's multiplied. These two terms are really the same, so it's multiplied by 2. So it's just minus secant square u, secant square v times du dv. Okay, so this was just a clever choice of factors. And similarly, this term here, the 1/4 v minus u whole square d omega square. V minus u whole square we've seen can already be written as secant square v, secant square u times sine square v minus u. So again, we've already pulled out a 1/4 secant square v, secant square u. So what we have left in brackets is sine square v minus u times d omega square. Okay, so we have this overall factor which multiplies a minus 2 du dv plus dv du plus sine square v minus u d omega square. Okay, and so we've taken, so what did we do? We started with t r theta phi. We transformed these to light cone coordinates uv. We compress the uv to a finite range. Okay, because we're working with light cone coordinates, this will preserve the causal structure as long as capital U is only a function of small u, capital V is only a function of small v. And then now what we'll do is we'll now return from this capital U, capital V. Okay, we will return to standard Cartesian-like coordinates, capital T, capital R. Okay, so this is the full procedure. Okay, so we switch to light cone coordinates, make them compact, and then switch back. Okay, so these are essentially the steps that you need to follow to get a Penrose diagram. Okay, so now we'll get T is V plus U, R is equal to V minus U. Okay, and we understand why, right? Because once you have a term like du dv, okay, if I write U is T plus R by 2, and V is T minus R by 2. Okay, if I take this, okay, then what I will end up getting is something like dt square minus dr square, or minus dt square plus dr square. Okay, and that's what we really want to get. Okay, we want to get something like that. We'll see why we want to get something. Okay. Okay. So now what we get is so now the other thing we have to be careful about is what is the range of these coordinates. Okay, what is the range of the coordinates capital T and capital R? So R goes between 0 and pi. Okay, because U and V went between minus pi by 2 to pi by 2. But we also have this constraint that U is less than or equal to V. Okay, since U is less than or equal to V, R must be greater than or equal to 0. Okay, and if you remember where this came from the fact that U is less than, small u is less than or equal to small v, and this came from the fact that this is T minus R and this is T plus R and R is positive. Okay, so this gives us U is less than or equal to V. At the upper end of the range, this is less than pi because the maximum value occurs when V is equal to pi by 2. Okay, which is when T goes to infinity. Okay, sorry. Yeah, when V is pi by 2 and U is also equal to pi by 2. Okay, so that's why you hit the maximum range, but you never actually hit that range, that maximum point. Okay, because that's the point at infinity that you brought in. Okay, so you're always strictly less than this pi. Okay, and similarly T. Okay, T can go between minus pi to pi. Okay, because T is V plus U. Okay, and both V and U can vary between minus pi by 2 and pi by 2. Okay, however, there is an additional constraint. Okay, what is the additional constraint? So the additional constraint turns out to be mod T plus R less than pi. Okay, now let's understand why we have this additional constraint. Okay, on our coordinates. The way we can understand this additional constraint is by looking at the original coordinates U and V. Okay, so we look at the coordinates U and V. So this is U and V, capital U and capital V. These are both going between minus pi by 2 to pi by 2, minus pi by 2 to pi by 2. Okay, now the region of these UV coordinates that is allowed is not the entire space, but only the region shaded in red. Okay, that is this region, the upper plane, because this corresponds to the region U is less than or equal to V. Where equality occurs at R is equal to 0, small r is equal to 0. Okay. Okay, so this entire region is U less than or equal to V. Okay. So this line corresponds to U equal to V. Okay, and these boundaries, which are at minus pi by 2, and this boundary here, you never actually reach those boundaries. Okay, these boundaries are actually, strictly speaking, not included. So these boundaries are not included. Okay, those boundaries are infinitely far away, right? So those are strictly not part. I mean, they're only coming in because tan inverse of infinity becomes pi by 2, right? And so infinity gets included at pi by 2. Okay, so this is what it looks like in UV space. In UV space, this is the region of UV that is allowed. Okay, but now we're switching to these TR coordinates. So if I look at the TR coordinates, T is V plus U. Okay, so changing V plus U moves you along this axis. Okay, these are changing V plus U, but this is constant V minus U. So this is T, okay, which is V plus U. So every point on this corresponds to changing capital T. Similarly, this is the R axis, okay, which corresponds to V minus U. Every point on this corresponds to changing V minus U, okay, but you're preserving V plus U. Okay, this is because this is a line V plus U is equal to 0. Okay, or in general, lines parallel to this are V plus U is constant. Okay, so this is the capital R axis. And this is the capital T axis, okay? And what we want to do is we want to express the constraint that we must lie in this upper triangle, but we want to express that constraint now not in terms of U and V. In terms of U and V, the constraint looks like U is less than or equal to V. But in terms of capital T and capital R, that constraint looks different. Okay, so how do we express that constraint? So the constraint is that we cannot cross this boundary and we cannot cross this boundary. Okay. This boundary corresponds to the point where R is equal to 0. Okay, and so we must have R greater than 0, greater than or equal to 0, but that we've already written down here. R greater than or equal to 0 is already telling us that U is less than or equal to V. Okay, it's these boundaries that we're now interested in. These are the non-trivial boundaries from the fact that we brought in infinity down to pi by 2. Okay, so how do we set these constraints? So the way we set these constraints, okay, on these regions is if I look at this point, this line here corresponds to V equal to pi by 2. Okay, now V can be written as T plus R by 2. Okay, and that is equal to pi by 2. So this boundary corresponds to T plus R is equal to pi. Oops. Okay. Similarly, this boundary is the point where U is equal to minus pi by 2. Okay, U is equal to minus pi by 2. So U is T minus R by 2, which is equal to minus pi by 2, or it's the constraint is T minus R is equal to minus pi, or equivalently minus T plus R is equal to pi. Okay, so our boundaries are minus T plus R is equal to pi and T plus R is equal to pi. Okay, and we want to lie below this boundary here and we want to lie to the right of this boundary here. Okay, so for yeah, so as we've seen, for T greater than 0, okay, that is if my T is positive, that is if I'm this way, okay, for T greater than 0, that is if I lie above this line, then the only relevant boundary condition is this one, okay, this one, that is the T plus R is equal to pi boundary condition. So T plus R must be less than pi, okay, if T is greater than 0. And similarly, if T is less than 0, okay, that is, again, this is my T axis, this is my T is equal to 0. Okay, and so if T is less than 0, the relevant boundary condition is this one. Okay, which corresponds to minus T plus R is equal to pi, and what we want is minus T plus R is less than pi. That case. Okay, so so this is true for T less than 0. So for T less than 0, we want minus T plus R less than pi. For T greater than 0, we want T plus R is less than pi. So together, these two conditions can be expressed as mod T plus R is less than pi. Okay, so putting these together, if for T less than 0, we want minus T plus R less than pi. For T greater than 0, we want T plus R less than pi. Putting them together, we want mod T plus R less than pi. Okay, so that's this non-trivial boundary condition that we get. Okay, so it's not that R and T span this full range. Okay, they span this restricted region, which in terms of R and T, which I've shown here, is only this triangle, okay, in R and T. So if I plot capital R and capital T, so this was the R axis, this was the T axis, okay, and we said that we're only in this restricted triangle. So what we can do is we can just rotate this diagram, okay, and we can draw R like this, T like this, okay, between pi minus pi, R goes to pi by 2, okay, and our diagram looks like this. Okay, so in the TR space, this is the region of TR coordinates that describe Minkowski space. Okay, and these white lines are the boundary, okay, which we brought in from infinity. Okay, which are not actually part of your Minkowski spacetime. Okay, they were brought in artificially from infinity. Okay, so now what we can do is we can look at the metric in these coordinates. That is, we can look at the metric in the capital T, capital R coordinates. So previously we were in the capital U, capital V coordinates. Now we switch to the capital T, capital R. Okay, and our metric in the capital V, capital U look like this. Okay, it was 1/4 secant square V secant square U minus 2 du dv plus dv du plus sine square V minus U d omega square. And now we express this du and dv in terms of or u and v in terms of t and r. Okay, so this term you can quite easily see will be proportional to dt square plus dr square. Okay, and this term v sine square v minus u will just become sine square r. Okay, and then this overall prefactor now has to be expressed in terms of t and r. Okay, so what we will get is a metric that looks like this. Okay, so our metric looks like this. It's some prefactor, which I'll write as omega to the minus 2 t r minus dt square plus dr square. Okay, this is coming from the du dv cross term plus sine square r d omega square. Okay, so note that this is a sine square r. It's not r square d omega square. It's sine square r d omega square. Okay, where r goes from 0 to pi. Okay, as we've already discussed. Okay, and now what is this prefactor? This prefactor is omega. Okay, 1 by omega square is 1/4 cosine square u cosine square v. Okay, this is the secant square u secant square v by 4 factor. So omega, the way we've defined it here, is 2 cosine u cosine v, which I now want to express in terms of capital T and capital R. Okay, so it's 2 cosine half t minus r cosine half t plus r. And using the another trigonometric identity, you can write this as cosine of t plus r. Okay. Okay, so this prefactor is just 1 over cosine t plus cosine r whole square. Okay, so this is the exact metric of Minkowski space. Okay, just expressed in these capital T and capital R coordinates. Okay, except using capital T and capital R coordinates. Okay. Now what you can do is, if you're only interested in the causal structure, okay, then you don't necessarily have to look at this metric. Okay, this metric is the correct full Minkowski metric, which means if you compute, even if you compute in these coordinates, you compute the Riemann curvature tensor or the Ricci curvature tensor or the Ricci scalar, you will get 0 because it's a flat metric. Okay, it's really a flat metric. It doesn't look flat because it has this prefactor, it has the sine square r, but really it's just a change of coordinates from Minkowski spacetime. So you're not going to get anything weird with the curvature. The curvature will just be 0. Okay, this is a flat metric. What we will do is move away from this flat metric by making a Weyl transformation. That is, we will actually change the metric. So we'll multiply the line element here by omega square tr to get rid of this factor. Okay, so we are changing our metric. Okay, as we discussed last time. Okay, this is to a conformally equivalent metric, or a conformally related metric rather. So our new line element, okay, will be related to the old line element. This is the Minkowski line element by this multiplication by this factor. Okay, and so we will get rid of that prefactor, and now we'll have minus dt square plus dr square plus sine square r d r omega square. Okay. This in general will not be a flat metric. Okay, because we multiplied by some conformal factor. Okay, just a point of terminology in Sean Carroll. Okay, this is, I mean, what we've seen in Nakahara is this transformation, this change of the metric is a wild transformation. This is not a conformal transformation. A conformal transformation preserves the metric, right? You're only changing the coordinates from one coordinate, one copy of the manifold to another. You're performing a map. Okay. Carroll calls this a conformal transformation. Okay, but this is not a conformal transformation according to our definition. This is what we call a wild transformation. Okay, we've actually changed the metric here. Okay, so what we will do is we will plot the Penrose diagram for the new metric. That is, we will just forget about that prefactor, which was multiplying the whole metric, and we'll just plot a Penrose diagram for this new metric. Okay, so a couple of points are, one is that the original metric was flat. The new metric will have curvature. Okay, the original metric was flat because it was Minkowski spacetime. The new metric will have curvature. Okay, for general Penrose diagrams, the original metric will have some curvature. The new metric will have a different curvature. Those two won't be the same, not even up to a coordinate transformation, because we have multiplied by an overall conformal factor. Okay, so the new metric in this particular case has curvature, unlike the Minkowski metric. Okay, so we can ask, what does this metric actually represent? Okay, this metric after multiplying by this conformal factor, what does it actually represent? Okay, what kind of space-time does it represent? And the answer is quite interesting. Okay, in this particular case, it turns out to be quite interesting. Okay, the new metric represents the natural inherited metric on R cross S3. Okay, so we've talked about the natural metric on S2, right, as ds square is equal to sine square theta, sorry, d theta square plus sine square theta d phi square, right? And where does this metric come from? This metric comes from the fact that you can think of S2 as being embedded inside R3, and then you think about inheriting the metric of that R3. Okay, so similarly, you can think about, so that is, you think about embedding it inside R3, right, where I have coordinates dx1 square plus dx2 square plus dx3 square. And I restrict myself to the surface with x1 square plus x2 square plus x3 square is equal to 1. Okay, when I make that restriction, then I will get this metric. Okay, this is the effective metric on S2. So similarly, we can think about S3, okay, as being embedded in R4. Okay, so a three-dimensional sphere is always embedded in one higher dimensional Euclidean space. And inside R4, we make the coordinate restriction that we are on this 3 sphere. That is, we require that x. So R4 has coordinates x1, x2, x3, x4. Okay, the metric on R4 is ds square is equal to dx1 square plus dx2 square plus dx3 square plus dx4 square. And we restrict ourselves to the surface, this unit sphere inside R4. Okay, so this will define a three-dimensional manifold embedded in R4. Okay, and we assume it's an isometric embedding. Okay, so so what we can do is to easily get the metric, okay, on this S3. What we can do is we can just assign coordinates. Okay, we can assign without loss of generality. X4 is cosine psi, x3 is sine psi cosine theta, x2 is sine psi sine theta cos phi, x1 is sine psi sine theta sine phi. Okay, this is a generalization of how you'd work with polar coordinates in higher dimensions. Okay, in higher Euclidean dimensions. So cosine psi is like your polar angle, okay, in along this new axis, this x4 axis. Okay, so here these polar angles psi and theta lie between 0 and pi, and the azimuthal angle it only comes at the end for the very last set of coordinates. Okay, you get an azimuthal angle which lies between 0 and 2 pi. Okay, and it's very easy to see if you substitute these in here that x4, x3, x2, x1, they satisfy this relationship. Okay, so this is without loss of generality. This is a coordinate transformation that you can write. Of course, it has its limitations. Just as polar coordinates, we know the limitations. North and south poles are not included. Okay, similarly, this also has those same limitations, but we understand exactly what those limitations are. Okay, So now the original metric on R4 was dx1 square plus dx2 square plus dx3 square plus dx4 square. You can show now by, we will now use the coordinates, polar coordinates, psi, theta, and phi. Okay, these are the inherited coordinates on S3. Okay, so we want to write the metric on S3 using these coordinates. Okay, and so we'll have the coordinates. You can show that this restricted to the S3 will now have a metric d psi square plus sine square psi d theta square plus sine square psi sine square theta d phi square. Okay, and you can imagine the generalization to even higher dimensions. Okay, so this, if I pull out the sine square psi factor common, this is d psi square plus sine square psi d omega 2 square. Okay, where this is the metric on a 2 sphere. Okay, so the metric on a 3 sphere is like d psi square plus sine square psi d omega 2 square. So this is a general rule. Okay, if I want the metric on an n-dimensional sphere, okay, I take one extra coordinate, which is the polar angle in the n+1 dimensional embedding. Okay, and I write d psi square, where that polar angle is psi, plus sine square psi times d omega square on the n-1 dimensional sphere. Okay, so you can see why that works. For example, for S2, right? For S2, what you get is d theta square is the polar angle plus sine square theta, and then the line element, okay, on an S1, but the line element on an S1 is just d phi square, okay, on a unit circle, okay, it's just d phi square. Okay, so this rule is very general and works for n-dimensional spheres. Okay, and this polar angle, this new polar angle that we've got, lies between 0 and pi. Okay, and psi is equal to pi represents the south pole, psi is equal to 0 represents the north pole. So psi is equal to pi represents the point where x1, x2, x3, x4, okay, are at 0, 0, 0, 0. Sorry, 0, 0, 0, minus 1. Okay, that's the south. What we mean by the generalization of the south pole. Okay, it's the point where x4 is equal to minus 1. Okay, so if you look at this metric, okay, if you look at this metric, and here psi goes between 0 and pi, okay, and theta and phi go between their usual values. So if you look at this metric, okay, what we obtained for our Minkowski metric after a Weyl transformation looks exactly like this. Okay, sorry, it was not this, it was sine square r. Okay, it was minus dt square. But this part was the interesting part. It was dr square plus sine square r d omega 2 square. Okay, and r again went from 0 to pi. Okay, in our case, we found r went between 0 to pi, but pi was not included. Okay, so it only went between 0. 0 was included. This corresponded to the point r is equal to 0. But it went only up to capital pi. Okay, sorry, it stopped short of pi. Okay, and the reason it stopped short of pi is because this was the boundary at infinity which we brought in. Okay, so now we see that the metric that we have here, okay, the metric that we found after making a Weyl transformation on the Minkowski metric, this is a metric on R cross S3. Okay, so this is really a metric on R cross S3 after making the Weyl transformation. And if we think of this R, okay, as this polar angle, okay, the 4D polar angle, made with this x4 axis. Okay, we see that we're basically got r cross S3 except for this point. Okay, that is capital R is equal to pi. That is, if we have ignored the south pole, if we had included the south pole, okay, we would have got the full r cross S3. But our original metric, okay, the original metric that we have, the Minkowski space metric, does not include that south pole of S3. Okay, it doesn't include the point with capital R is equal to pi. Okay, so it's something like R cross S3 where I remove the south pole from S3. Okay, so to give you an analogy, okay, of what we mean by that, for example, suppose we look at R2. Okay, if we look at R2, and if we take all the points at infinity, Okay, and we say that all these points at infinity really correspond to the same point. Okay, so this is exactly what we did when we did the stereographic projection. So when you took an S2 and we project it onto the plane, okay, the north pole gets projected off to infinity. North pole gets projected off to infinity. Okay, and that's not part of your stereographic projection. But if I identify R2 union the point at infinity, okay, then I get back my 2 sphere. Okay, so similarly, we've got a 3 sphere. If we remove the point at infinity, okay, then we'll just get R3. Okay, so we kind of remove that point at infinity. Okay, if you want Minkowski spacetime. Okay, so now our basically the metric that we had written down is minus dt square plus dr square plus sine square r d omega square. Okay, this was we said that this is the metric on r cross s3 for minus infinity less than t less than infinity. So the full range of r cross s3 is, we assume that t goes between minus infinity to infinity. That is, t has coordinates on the real line, and on s3, okay, r goes between 0 to pi. Okay, and strictly speaking, pi is also included if I want to include the south pole. Okay, and then I also have theta and pi and theta and phi as usual. Okay, now this metric, okay, on r cross s3, this is the standard metric that you would have on r cross s3. S3 has a standard metric that is inherited from embedding in R4. Okay, capital R is just your time coordinate. Okay, so this full metric with this full range of coordinates, this describes something called the Einstein static universe. What is the Einstein static universe? Well, it's basically a universe which is, instead of being on R4, is on R cross S3. Okay, that is, it is a closed universe. Okay, that is, instead of space being in R3, space is compactified. Okay, it's the union of R3 and the point at infinity. When you close up space, when you wrap it up into this 3 sphere. Okay. And it's called static because there are generalizations of this where you can have an expanding 3 sphere. Okay, so that is, I can take the spatial part and make it put a prefactor, which is a function of time. And so if I change this as a function of time, I'm changing the radius of that 3 sphere. Okay, so just as if I had not taken a unit sphere, okay, in 2 dimensions, if we take a sphere of radius capital R, okay, we would have a metric like this. Or if we choose a radius capital A or small a, we would have it would look like this. Now, the only thing is we make the radius of the sphere a function of time. Okay, so that would be a spatially expanding or spatially contracting universe. Since we've chosen a of t to be a constant here, that's why it's called a static universe. Okay, so it's a closed, non-expanding universe. Okay, for this full range of coordinates, it's a closed, non-expanding universe. Okay. However, the portion of this, only a portion of this full closed non-expanding universe is related to Minkowski spacetime, okay, by this Weyl transformation. So we take our Weyl transformation of the Minkowski metric, and then we saw that our range of t and r coordinates are restricted. They must satisfy this minus pi less than t less than pi, 0 less than or equal to r less than pi, and mod t plus r less than pi. Okay, we have these 3 conditions on t and r. As opposed to letting t run from minus infinity to infinity, letting r run from 0 to pi without any additional condition. Okay. So what we can do is we can represent the full r cross S3, which is this Einstein static universe. We can represent it pictorially, and we can show that only a portion of it, okay, we can show the portion of it that corresponds to the space-time that is conformally related to Minkowski space-time. Okay, so the way we'll represent this r cross S3 is we'll actually use an r cross S1. Okay, r is a line, S1 is a circle. So at every r, if we have a circle, what we actually get is a cylinder. Okay, so this is that cylinder. This is r cross S1. Okay, so and now what we do is we mark some points, okay, on this. So the R direction, which is this way, corresponds to the time direction, okay, this capital T. So capital T in the full Einstein static universe runs from minus infinity all the way up to infinity. Okay, and capital R, which is like that polar angle psi, okay, this only runs from 0 to pi. It only runs from 0 to pi. Now, the thing is, we are choosing S3, okay? On S3, the polar angle runs from 0 to pi. If instead of S3, we had taken S1, which is what we have done here, okay, then it would not be a polar angle anymore. It would be an azimuthal angle and it would run from 0 to 2 pi, okay, which is why we've shown a full circle here running from 0 to 2 pi. Okay, so this actually represents the coordinate psi, or what we had written as capital R earlier. Okay, it's the polar 4D polar angle. Okay, okay, so I've shown R is equal to 0 and R is equal to pi. Okay, and strictly speaking, you know, if this was an S1 only, then psi would, or this R would run from 0 to 2 pi. Okay, which is why I've shown a full circle. Okay, but if you're looking at an S3, then you only have 0 to pi. Okay, you only go like this. Okay, now what else do we have? Okay, so now if we think about an S3, okay, what we're saying is now each point on this cylinder, okay, on the surface of the cylinder, each point on the surface of the cylinder, I've specified a t coordinate and I've specified a polar angle psi. So the things that are remaining to specify are theta and phi, that means that each point on the cylinder actually corresponds to an S2. Okay, each point of the cylinder corresponds to a 2-sphere. Okay, now let's come to the region of the cylinder. So this full cylinder, okay, where each point is interpreted as an S2, this full cylinder represents the full Einstein static universe, where T is allowed to run over its full range from minus infinity to infinity. Capital R is allowed to run over its full range from 0 to 2 pi or 0 to pi, okay, when we're thinking about an S3. Okay, now we're going to look at only a region of this, only a restricted region of this. The restriction is that T should lie between minus pi to pi. This is the first restriction. So that is, we draw the circle with T is equal to pi. Okay, this is the region where T is equal to pi. This is the region where T is equal to minus pi. Remember, this is the T axis. Okay, so T is equal to pi will be one point here. T is equal to minus pi will be another point here. And I mean, of course, this entire circle has coordinates T is equal to pi or minus pi. So these are the points T is equal to pi or minus pi. So my entire region of which satisfies this condition must lie between these two circles. Okay, so it must lie on this portion of the cylinder. Now, the second condition is that 0 is less than or equal to R less than pi. Okay, which means that we are, let's say, on half a cylinder. That is, strictly speaking, we're only on, let's say, the right half of the cylinder, not on the left half of the cylinder. And moreover, the point R is equal to pi is not included. Only the point R is equal to 0 is included, which means that all of these points are actually included, but the opposite line on the cylinder, that is not included. Okay, that is not included. Now, in addition to this, we have this other non-trivial condition that mod T plus R is less than pi. Okay? Mod T plus R is less than pi. That's a bit harder to visualize, but I've shown it with these red lines. Okay, what we can really do is you can unwrap the cylinder. Okay, so now you basically have T and R. Okay, and if I unwrap the cylinder, this is R is 0, this is R is pi. Okay, and then, I mean, of course, the full cylinder goes up to 2 pi if I unwrap the cylinder. And now if I look at this, T plus R is less than pi, okay, is this condition. That T plus R is less than pi is this condition. Okay, it's a triangle like this and a triangle like this. Okay, and we're only interested in this region. T plus R is less than or equal to pi. So this region here, if I fold the cylinder again, okay, would correspond to, here is the base of the triangle, and I'm wrapping the triangle around the cylinder. Okay, and here's the vertex of the triangle, okay, which is this vertex here at R is equal to pi. Okay, and similarly on the other side also I have the same triangle, okay, which is meeting over here at R is equal to pi. Is this picture clear? Any questions about this picture?
Yeah, it's clear. Just one. question.
Yeah.
So it's symmetric about the plane that passes through r equal to 0, r equal to pi lines, right? The entire thing.
It's symmetric. What do you mean by symmetric? The triangles?
No, the whole space is because you're saying r because r is only going from 0 to pi.
Yeah.
On the other side also we're in some sense going in the same, but like here we're going clockwise and there we're going anti-clockwise from 0 to pi.
Right. But so strictly speaking, when we're on r cross s3 as opposed to r cross s1, then we are only considering the region 0 less than or equal to r less than pi. Okay, so we are considering this line. We're not considering the left half of the cylinder. We're going around this way. And the point at pi, which is just the vertex of that triangle, that is not included. This is not included.
Okay. So this should be the same kind of diagram we would draw for r cross s2 and s as well, but each point would not represent an s2 circle.
Yeah,
which
so
is why we keep the whole thing instead of cutting it.
For r cross s1 only, you would use the full use the full thing.
Okay.
Okay, but any higher dimensional space-time, I mean, instead of an S2, let's say you have an S3 or an S4 or an S5.
Okay, so my question was just why don't we just draw a half cylinder instead of a full cylinder? Like
you could draw a half cylinder, yeah.
Okay.
You could draw a half cylinder. I mean, it's just easy to understand when you draw the full cylinder.
Yeah, got it. Thank
you. Strictly speaking, you should draw a half cylinder if you're talking about R cross S3, and you want each point to represent an S2. Okay. Okay. The other point is that the boundary where t plus r is equal to pi, which is the top of this triangle, right? This is the point where t plus r is equal to pi. And this is the point, and this line is minus t plus r is equal to pi. These boundaries are also not included. Okay, these boundaries are also not part of your, they're not part of your coordinates. Okay, they're not part of the coordinates. What are these the coordinates of? Remember, we started with the Minkowski spacetime on which we made a Weyl transformation. And there the metric looked like this. It looked like the metric of the Einstein static universe, except we have a restricted range of coordinates. Okay, the full Einstein static universe has everything on the cylinder, okay, or everything on the half cylinder. The Minkowski spacetime after making the Weyl transformation is restricted only to this region inside this triangle wrapped around the cylinder. Okay, so the interior of the region in red is related to Minkowski spacetime by a Weyl transformation. Okay, and this Minkowski space on R4 does not include the point r is equal to pi. Okay, r is equal to pi is spatial infinity. Okay, but it does include this r is equal to 0. Okay, and it does not also include these boundaries. R plus mod t is equal to pi. That is those two arms of the triangle are not included. Okay, so what you can do is you unroll that region into the cylinder, okay, to represent Minkowski spacetime. So this is the t-axis. This is the r-axis. T goes from minus pi by 2 to pi by 2. R goes from 0 to pi. Okay, and you mark certain points. Okay, so you mark this as I minus, small I minus. You mark this as small I plus. You mark this point as I0. Okay, and you mark this as scri. This is called scri plus. It's script I plus. Okay, in short, it's called scri plus. Okay, and this is called scri minus. Or script I minus. Oops. So these boundaries, okay, these boundaries, that is script I minus. Script I minus, I0, script I plus, I minus. Okay, these boundaries are referred to as conformal infinity. Okay, these are actually not part of your Minkowski spacetime. They were artificially brought in when you compactified the u and v coordinates, okay, and pulled in u is infinity and v is infinity and made them finite. Okay, so these represent the boundary, okay, and this is called conformal infinity. And if you take the union of the interior of this region, okay, including this point. So these correspond to the points where the r is equal to 0. Okay, and we already discussed how you can actually include them in. These points can be included, but the boundary here, this line, this point, this line, okay, that entire boundary, it was actually not part of your Minkowski spacetime. If you take the union of your Minkowski spacetime plus the boundary, the conformal boundary, okay, or conformal infinity, you get what is called the conformal compactification of the spacetime. Okay, so the union of these two, the Minkowski spacetime plus its conformal boundary, or in general any spacetime with its conformal boundary, you get what is called a conformal compactification of the spacetime. Okay, this conformal compactification is not the typical manifold that we looked at. Rather, it's a manifold with a boundary. Okay, it has so topologically, it is like being on a disk with the boundary included. Okay, so it's not an open ball anymore, right? It's a closed set because it includes the boundary. So this is a manifold with a boundary. Okay, if you include the conformal boundary. Okay. Now these conformal boundaries are given special names. Okay, so this point at I plus, okay, is called future time-like infinity. Okay, so this corresponds to the point where capital T is pi and capital R is equal to 0. Okay, and similarly, this point here, I0, is called space-like infinity. Okay, this corresponds to the point T is equal to 0, capital R is equal to pi. And this point is called time-like past infinity. Okay, so this is time-like future infinity. This is time-like past infinity. Sorry, past time-like infinity. Okay, which is at T is equal to minus pi, R is equal to 0. Okay, these are single points. Okay, these are single points. Okay, this conformal boundary is a single point. However, these boundaries, scri minus and scri plus, okay, these boundaries are at T is equal to pi minus R, where the R goes from 0 to pi. Okay, this is called future null infinity. Okay, so there's a range of capital R values over here. Okay, and T is correspondingly given by pi minus R. And this is called future null infinity. Okay, and scri minus is called past null infinity. Past time like null infinity. Okay, so these are actually null surfaces. These are not points. These are null surfaces. Okay, because each of these points is now associated with an S2. Okay. Yeah, so the topology of these scri plus and scri minus are roughly like R cross S2. Okay. So each point on I plus and I minus is associated with an S2. But these endpoints, okay, no longer actually have an S2 associated with them. This I plus, because you see this is at R is equal to 0 already. Okay, this is already at R is equal to 0. So there is no two sphere associated with this. This is actually just a single point in space-time. And similarly, this I0 is just a single point. Okay, it's not part of your space-time. It's part of the conformal boundary. Okay, or conformal infinity. Okay, the other point, which is really important, is the radial null geodesics travel at 45 degrees on this diagram. Okay, because on this diagram, we have ds square is equal to minus dt square plus dr square. Okay, so so if I fix or plus sine square r d omega 2 square. So if I fix my angles again, if I fix my polar angle, 3D polar angle and phi, then this is 0. Okay, this doesn't change. So if I only look at radial null curves will follow dr dt is plus minus 1. Okay, so once again, null curves will always move at 45 degrees. Okay, so null curves will always move at 45 degrees. That is, null curves will always move like this or like this. So this is called an incoming null geodesic, and this one is an outgoing null geodesic. Okay, and that's why you see that scri minus is called past null infinity, because null geodesics start here. Okay, and they will travel in such a way that they will end up here. This is future null infinity. And similarly, any point that I take, okay, if I want to draw the future light cone, all I have to draw are 45-degree lines. Okay, so this is the future light cone of this point, and this is the past light cone. Okay, with some work, you can also figure out what are the surfaces with what are the trajectories with r is equal to constant and t is equal to constant. R is equal to constant trajectories will look like this. Okay, these are r is equal to constant, these red curves, and these magenta or pink curves are the t is equal to constant. Okay, these purple curves, these are t is equal to constant. So this one, this one, this one, these are constant t slices. Okay, so we know that r is equal to constant. Okay, are null are time-like geodesics, right? These correspond to particles at rest in Minkowski spacetime. So you see that particles at rest in Minkowski spacetime will start at I minus, okay, and they will end up at I plus. Okay, and this will be true even if they're moving with constant velocity. They'll start at I minus and end up at I plus. Okay, they will always start at I minus and end at I plus. So all time-like geodesics, that is geodesics for massive particles, okay, which are not null, they will always begin at I minus and they will always end at I plus. Okay, so this is some peculiarity of the conformal infinity that we brought in. Okay, all the time-like geodesics will start here and end here. Okay, all the spatial geodesics will begin and end at I0. Okay, they will both begin and end at I0. This is spatial infinity. This is coming in. This is t is equal to constant, right? This is t is equal to constant, looks like this. Okay, so they will come in and then they will go back out, okay, to here, because this is just the point r is equal to 0. Okay, so I mean, they're going out, you know, in a different direction. They're going in line. So they come in at theta is equal to 0 and exit at theta is equal to pi. Okay, so come in at theta is equal to 0, exit at theta is equal to pi. This is a radial, a spatial geodesic. Okay, so this is just, let's say the line x is equal to or z is equal to const. Where z is changing. Okay, so you're just changing your z coordinate. So that could correspond to something like this. Okay, so this pink line. So these start at the singular point. Okay, singular point from conformal infinity at I0, and they end at I0 as well. And null geodesics are more interesting. Okay, null geodesics can begin at scry minus. Okay, you can have a null geodesic which starts here, goes here, and then goes off to scry plus. Okay, so null geodesics begin at scry minus and end at scry plus. Remember that null geodesics will still travel at 45-degree lines on this diagram. Okay, so we can also have non-geodesic time-like curves. Okay, so you can have a so you can imagine that, let's say this observer, okay, who's traveling along some r is equal to constant, instead of being inertial, decides to accelerate. Okay, and they accelerate, and asymptotically, let's say they approach the speed of light. So asymptotically, okay, they will sort of end up on scry plus. Okay, they will end up on scry plus. Okay, because they'll be almost on a light-like trajectory. So all so non-geodesic time-like curves that end at null yeah, they can end at null infinity, future null infinity, that is on scry plus, if they become asymptotically null. Okay. Okay, so now the point is that if you look at this Penrose diagram, a couple of things. One is that we don't really care what the actual metric is. Okay, we don't really care what the actual metric is. We are interested in the causality structure. The metric is telling you distance measures. The metric is also telling you what the geodesics are. Okay, but we're not interested in those. We're just interested in the causality structure. Okay, that is what is the future of any point, what is the past of any point, and so on. Okay, so we're not interested in the actual distances. So whether I choose this metric, which is after a while transformation, or whether we choose the metric with this overall factor, omega to the -2 tr times minus dt square plus dr square, and this was the metric of Minkowski spacetime, the causal structure will still be the same. Okay, the causal structure will still be the same. The global structure is still the same. Okay, the global structure being that it's contained in this finite region, and we've understood what the asymptotic infinities are. Okay, we understood the conformal infinities. So it doesn't really matter whether we think about this metric before or after the while rescaling. Okay, as far as the purposes of understanding causality and the global structure of the spacetime. Okay, if you do want to understand the details of what is the distance between two spacetime points, yes, the details of the metric matter. Okay, if you want to study the geodesics, yes, the details of the metric matter. Okay, but if you're not asking those questions, then if you're only interested in causality, okay, then we're only interested in the null geodesics, and the null geodesics are the same whether you use this metric or this metric. Okay. I mean, ds square will be 0 is the same for dt by dr is equal to plus minus 1. Okay, we'll still give you ds square is 0. Okay, for radial null geodesics. Okay, and so what you can do very easily with Penrose diagram. So this is called a Penrose diagram. This is the Penrose diagram for Minkowski spacetime. Okay, so you can see whether the past or future light cones of any two spacetime points intersect using these Penrose diagrams. In Minkowski spacetime, if I choose any 2 points, the past and future, I mean, either the past light cones will intersect or the future light cones will intersect. Like this will lie in either in the future or the past of each other. Okay, so so in Minkowski spacetime, it's always true that any two spacetime points are causally connected. Okay, but in general spacetime points, it's not necessarily true. Okay, that is. Sorry, in this Penrose diagram, they are causally connected. Okay, all these points in the Penrose diagram are causally connected. Yeah, sorry, not causally connected. Causally connected means even 2 points which are spatially separated, let's say they lie on the same r is equal to constant, they will have a common point in their past, which means that they could have both been influenced by, so their past light cones intersect, which tells you that they have a common point in their past, which could have had an effect on both of them. Okay, so that's what we mean by in their past, their light cones would have intersected, or in the future, the light cones will intersect. Okay, but that's not going to be true in general spacetimes. And these Penrose diagrams are especially useful when you go to things like curved spacetimes, like the Schwarzschild black hole that we had seen. Okay, because there you're really trying to understand the causal structure. In Minkowski spacetime, the causal structure is simple. Okay, in these more complicated spacetimes, like Schwarzschild spacetime. So this is what the Penrose diagram looks like. I won't go through it. Okay, I won't go through the derivation. You can look it up. It's quite easy because we've already derived in class these Kruskal-Zekeres coordinates. Okay, and basically the idea is, again, starting with Kruskal-Zekeres coordinates, the main point is that these are global coordinates. They cover the full spacetime, right? And if you remember, in the full spacetime, in this capital T, capital R, what we had is sort of, we had a region like this. We had a singularity here. We had a singularity here on this hyperbola where minus t square plus r square is equal to 1. Okay, these define two arms of a hyperbola. This corresponds to a white hole singularity. This corresponds to a black hole singularity. Okay, there's a region 1 here, which is our universe. There's a region 2 here, which is the interior of the black hole. Region 3 is the interior of the white hole. Region 4 was the parallel universe. Okay, and this region is the black hole singularity. Okay, so this region of spacetime doesn't exist. Okay, beyond this. And similarly, this region of spacetime doesn't exist. Okay, so these TR coordinates which lie beyond this hyperbola arm don't exist. Okay, and what you have to do is exactly the same procedure. Okay, so the first point is that you have global coordinates. Capital T, capital R, the Kruskal-Zekeres coordinates cover the full spacetime. Now, instead of directly compactifying this, you switch to light cone versions of these. Okay. And then from the light cone versions, you compactify. Okay, so you'll get some u prime, v prime. And then you again switch back to light coordinates. Sorry, space, usual standard coordinates. Okay, so it's the same procedure that you will follow here. Okay, and when you do this, okay, the Penrose diagram that you get will look like this. Okay, everything in this, so there's sort of these two diamonds or these two squares, which are here, this one and this one. This corresponds to region 1, this corresponds to region 4. This corresponds, so this 1 is our universe, 4 is the parallel universe. This is region 2, which is the interior of the black hole. This is region 3, which is the interior of the white hole. This entire region corresponds to the white hole singularity at r is equal to 0. This entire region corresponds to singularity, the black hole singularity. Okay, where you cannot determine what happens beyond that in classical GR. Okay, outside of the black hole in region 1, you will still have this I plus, I minus, scry minus, scry plus, and I0. Okay, and similarly, you'll have an I0, I plus, I minus, scry minus, scry plus for the parallel universe. Okay, and R is equal to constant curves will look like this. Okay, they will begin and end at I0. T is equal to constant curves will start at I minus and end at I plus. Okay, but now you see that the causal structure is more interesting because we know that things, if I draw null geodesics from here, we know that these null geodesics can now enter into the black hole. Okay, they can enter into the black hole. So anything which goes in like this, and we know that this is the Schwarzschild horizon. Okay, and since this is a null geodesic, and you can clearly see that it's null. Okay, this is a null surface, and you can clearly see that it's null on the Penrose diagram. On the Penrose diagram, this is a 45-degree line. Okay, and now anything that crosses this, okay, because at best it can travel. If anything crosses this, at best it can now travel on a null geodesic. It can never escape the black hole. Okay, you can see that very clearly now. That any point that is headed, once it crosses this horizon, okay, it must hit the singularity here. Okay, there's no way to escape the singularity. You can see that causal structure much more clearly on a Penrose diagram. Okay. Okay. So now the conformal boundary for our universe is still the same. Okay. So any space-time which has the same conformal boundary as Minkowski space, that is, it has the same scry plus, scry minus, I0, space like infinity, past null infinity, future null infinity. Such a space-time is called asymptotically flat. Okay, so asymptotically, it looks like Minkowski space-time. But inside, the causality structure is quite different. You see that there are these singularities. You can end up at the singularity if you cross the black hole horizon. Okay, so the black hole and the white hole horizons also become much more apparent in the Penrose diagram. The singularities become apparent, and the global structure, that is the full space-time, is now captured in this compact region. The causal structure is also much more easily visible, okay, when you use this kind of Penrose diagram. Okay, and finally, okay, I'll just show you for FRW cosmology. We haven't really done cosmological models, but I did tell you about some kind of model like this, right, where I put in, so if I set this A of t to 1, this is standard Minkowski space. And now if I put in a square t, it's basically Minkowski space where space is stretching as a function of time. Okay, so the metric on my spatial slices is stretching as a function of time. A of t increases, let's say, as time passes. So in this case, the important point is that t is equal to 0, a of t goes to 0. So you have a singularity. Okay. So these kind of models of metric spaces that look like this, these are called FRW models. Okay, they show up in certain cosmological models. These are special cases of what is called spatially flat FRW cosmology. Okay, as opposed to the, let's say, the Einstein universe, non-static Einstein universe, which is spatially closed. Okay. Okay, and now the thing is the asymptotic structure of this looks very different. Okay, so you still have an I0, you have a scry plus, which is future null infinity, and you have I plus, which is future time like infinity. But now your past null infinity, okay, is past time like infinity is I minus, which is now not a point anymore. okay, but an entire region. Okay, it has some topology again of, I think, R cross S2. Okay, so now this does not have the asymptotic structure of Minkowski spacetime, because as I go back towards t is equal to 0, as I go backwards in time towards t is equal to 0, so these are surfaces of constant constant R. This is constant R. Okay, and I'm going back in t as I go this way. Okay, at t is equal to 0, I hit the singularity. The singularity is not actually part of my spacetime. Okay, and so as I go backwards, I hit that singularity, and this is a different causal structure than that of Minkowski spacetime. Things originate at a singularity, and the singularity is called the Big Bang. Okay, where again your predictions of GR break down at what happens at this Big Bang. So very immediately, when you look at a Penrose diagram like this, you can very quickly make out, okay, whether the space is asymptotically Minkowski, what the causal structure is, where the where the singularities are, and so on. Okay, so just some minor points. Okay, so we had a metric, then we made a change, a wild transformation to get a different metric. When you make such a transformation, the angles between vectors are the same. Okay, as we've seen, if you take a wild transformed metric, you will still get the same angles between vectors. But we used in particular the fact that null vectors, if you take the dot product of a null vector with itself, okay, this is 0. Okay, and that angle between them, which is 0, that is preserved. Okay, no matter which metric you use, whether you use this metric or this metric. The geodesics are not the same. Okay, so if I want to ask questions about geodesics, I really do need to know what the conformal prefactor was. Okay, but in general, I don't need to worry about it. Okay, I don't need to know if I'm not interested in the exact trajectories that particles follow. If I'm only interested in the causal structure and the global structure, okay, then that's when Penrose diagrams are used. Okay, stop here. Any questions?
Sir, when you were changing from coordinates small t to null coordinates, then compactification to capital U and capital V coordinates, then to capital T to capital R. You said that now, like, so how do we know that capital T and capital T is time-like coordinate and R capital R is space-like coordinate? Like, we're mixing the T and R. How how do we know that? Yes, yes.
Okay. So I mean, essentially, the idea is that in light-like coordinates, these coordinates will look like du dv. Okay, and the metric involving u and v, this part will look like du dv, and again here it will look like du prime dv prime. Okay, so I'll start with something like this. Times may be a factor. Okay, then I will go to something like this. Okay, and then I will compactify. Okay, so we'll see that you'll get something like secant square u, secant square v times du prime dv prime. Okay, something like this. Okay, and now we can always make a transformation. This is all a prefactor, right? So this part can always be transformed back to something like this, right? So the key point is, once I know the null structure looks like this, then I can always get back something which looks like standard space-time coordinates by doing u prime is t minus r by 2 and v prime is t plus r by 2.
Okay. Okay.
Right? Yeah.
Sir, why is the topology of like the sky minus or sky plus r cross s2? Why not r2 cross s2? Because there are all we need 2 points and one s2.
We need 2 points. What do you mean by 2 points?
I mean, even in TR coordinates, like any point on I my sky minus, I mean, we need capital T and capital R. So 2 real numbers.
No, but there's a unique, any point on Scry plus is given by a particular value of capital T and capital R, right?
Oh, yes, sir.
Or equivalently, if I want all of the points on Scry plus, I only need to specify the capital R values because the capital T values are automatically determined, right?
Yeah, from that condition of t.
Yeah, T is equal to pi minus R.
Yeah.
So basically, I'll specify R and I'll specify the S2 coordinate.
Yeah. Yes.
That's why its topology is R cross S2. It's only topologically equivalent, right? It's not equivalent to R cross S2 because this has a finite range and the metric is different. Topologically, Sky plus is R cross S2.
Sir, and one more thing, like sir, we are saying like when we are using some conformally related metric, we are saying that the geodesics will be different because we know that like in code, like in terms of coordinates, the geodesic equation will have Christopher symbol. So the Christopher symbol depends on the metric. So now we'll have to use new Christopher symbols in terms of G bar. So that is why we are saying that the geodesics will be different. Right?
Right. Yeah, I mean, essentially, think about it. Geodesic is the shortest distance, right? The distances have changed when you change the metric. But the null geodesics remain the same. Okay, any other questions? All right, let me just stop the recording.